So in this course, we'll discuss about signals and systems, and I'm Lakshmi Narasimhan, and I'll take you through this course where we'll model electronic systems using signals and concepts that we'll study here mathematically through various tools and try to understand and analyze these systems, and then also which will help us in the design of these systems. Let's see the outline of this course. So the outline of this course is split into 6 modules, as you can see in this slide. So there are different modules here which will move in sequence. The first module is about continuous and discrete time signals. We'll first talk about signals and then see what they are, how they are modeled, how they are represented. The second model is about systems. Once again, we'll see how they are modeled, how they are represented, and so on. And the third one is about a very specific kind of system, what we call as an LTI system. And once we see the details about the signals and systems, then we'll see how to analyze them, how to model them. The fourth one will be about a particular kind of representation of signals and systems. And the last two are about a way of analyzing these signals and these systems using a particular kind of mathematical tool called as the Fourier transform and the Laplace transform. The textbook that we'll be using for this course is shown here. It's Linear Systems and Signals, which is authored by B.P. Lathi and Roger Green. This is what we'll follow for this course. Let's start and let's introduce ourselves to signals and systems. First, what are signals? A signal is basically nothing but a function. What is a function? A function, let's say we represent a function by f of x. The x here is an independent variable. So what do we mean by independent variable? It is not under our control. It keeps changing according to some independent rule. So we do not get to control what is x. But then the moment an x value is given, the value of f is completely dependent upon this value x takes. So the moment I say that x is equal to, let's say, some 10, then the value of f gets fixed. F of 10 is something which is already fixed. That depends upon this function. How do we visualize this function? We visualize it through a graph, something that is given here. So we have an x-axis, we have an y-axis. The x-axis is where we typically put in the independent variable. For example, independent variables could be time or frequency or position. So a simple example is, let's say you take a circuit and then you connect a battery to it, and then let's say there is a resistor, and then you try to measure the voltage across here, or let's say you try to measure the voltage across the resistor. Now what do you observe? You observe something which is a function of time. So you can plot in the x-axis some time, and you can plot the voltage that you see here. In other words, you're plotting the voltage as a function of time. It can probably be something like this. It can fluctuate depending upon the battery level and so on. So what we have essentially done here is we have visualized a signal, and that signal is the voltage signal across this resistor, and we have plotted that signal as a function of time t, where t is on the x-axis and on the y-axis we have the voltage signal. So the independent variable here is the time and the dependent variable here is the voltage. Now you can change this also to be current or the power or the heat that is dissipated. So the dependent variable can keep changing, the independent variable can also keep changing. So what would be the different notion of an independent variable? Let's say now I have frequency here. Now we can say, let's say there is a capacitor in this circuit also. Okay. Now the resistance of a capacitor, as you all know, would keep changing with the frequency of the voltage. So if you try to plot the resistance of the capacitor, then depending upon the frequency, then the resistance will keep changing. So if you have a zero frequency, which is a DC, then the resistance here would be very high. So it should be the other way around. And for a frequency which is really high, which is an AC signal, the resistance will be really small. So the resistance will keep changing with the frequency. So this is another kind of a signal where the independent variable is frequency and the dependent variable is something that is a function of the frequency. In this case, it is the resistance, which is a function of frequency. And similarly, let's say you are moving inside a room or you are driving somewhere, you turn on your GPS, then you can measure what happens to you as you move from somewhere to somewhere. Let's say I want to uh, plot your speed as a function of your position. So when you are in, let's say, some location, your speed is so much, and when you move to a different location, your speed changes to something else. So you can plot your speed or your temperature or your energy, whatever, as a function of your position as well. So we can have the independent variable to be time or frequency or position, and something that changes in relation to this independent variable can be plotted as something as a dependent value on the y-axis. So this is what we call as a signal. Okay. Typically, this dependent value can be amplitude or phase or anything. So if you take a circuit, what we usually end up plotting on the x-axis is either the time or the frequency, and usually what happens on the y-axis is either the voltage or the current or the power or the resistance or the impedance offered by these circuits. So this is all what typically appears as a signal in an electronic circuit. So let's see some more examples. How do we observe the signal visually in real life? So we just drew a graph, right? So how do we visualize it in physically? Typically we'll use an oscilloscope. What do? You just connect this probe to your circuit, and then you visualize what is happening here as a function of time. So this is what we'll use for visualization typically with circuits. Okay, and then what do we have here? So we have here a temperature sensor. What does it do? The temperature sensor gives you the temperature in a particular location. So basically this has some connected to battery, this is ground, and this gives you the voltage signal, which is directly proportional to the temperature. So if you plot the voltage that is coming across this pin, then you connect this probably to an oscilloscope, something like this, then you see across time, you see some signal, something that is varying, so that voltage level that is varying. This voltage level is directly proportional to the temperature of this room where the sensor is located. Now here, the next example, we have a light dependent resistor, LDR. So you connect this once again to a voltage source and then see what is the variation in the voltage that you get across this resistor, and then plot it across in a plot like this. So plot the resistance here. This directly corresponds to the amount of light that is incident on this element. And another sensor we have here, which is a proximity sensor, an ultrasonics based proximity sensor. You connect this to a voltage source, ground, and then the amount of echo that needs to go in, and then this is the output. So you connect this pin to an oscilloscope, you can probably end up seeing a signal something like this. You can plot across time. So what do these different signals that we got from different sensors indicate? The first one indicated the temperature that is in the room, the second one indicated the amount of light that was present in the room, and third one indicated the amount of objects that are closer to you. The proximity of these objects are indicated by these signals. So these are all simply nothing but something which is varying with time. And how do you visualize it? You visualize it probably using an oscilloscope, using a plot. All of this eventually looks like something plotted along the x-axis is the independent variable, and something that is plotted along the y-axis is what you observed. So along this y-axis, this x of t could be the voltage which is proportional to the temperature, or it could be the voltage that is proportional to the light, or it could be the voltage that is proportional to this proximity. So all of this eventually can be represented as simply nothing but a signal, and that signal is nothing but a function of the independent variable and what you are observing. So at the end of the day, anything that you observe using these circuits and sensors could be modeled using the signal that we have here, which is nothing but a function of some dependent variable, that is time. Okay, and there is also a different example here which we'll keep using repeatedly, and that example here is recording an audio. Very simple circuit which we can use for recording audio. Basically has a microphone connected to a battery, and there is a capacitor, right? So the audio comes in through here, so that is a signal, and eventually how do you get this audio as an electrical signal? You just connect this point to your oscilloscope. What do you observe? you observe probably something like this that we have here. This is your audio signal. You will probably observe something like this, and this can represent your signal. So what we have now seen is different kinds of signals and how we end up representing them as a function of an independent variable. Typically, it will be time or frequency for us. Okay. How do you generate signals in your hand now? So there are several ways of generating these signals. The very phone that you have could be used to see real life signals in many different ways. So one helpful app is this Arduino Science Journal app, as you can see here. This is a free app that you can download for your iPhone or Android, and it connects to all the sensors in your phone. So your phone has a light sensor, it has a magnetic sensor, it has an accelerometer, and it also has a microphone. So the signals from all these sensors could be obtained using this app. So this is a nice way of visualizing signals in real life. Okay? So play around with this app and you will get an idea of what are the different kinds of signals, how you see, how you obtain these signals. So there are some examples here. This is a temperature sensor, this is a light sensor, and this is some inertial sensor which gives you the position and so on. So you can probably collect some signals using this app, and then later using the tools that we learn in this course, analyze these signals. Okay, now that we are done with signals, or we have been introduced to signals, let's try to understand what are systems. Systems is basically nothing but a box. We can say that a system could be simply as something that takes an input, processes it somehow, and then produces an output. So any box that takes an input and then does some processing to it and then produces an output is called a system. Okay. Now, what are examples of systems? We saw a simple circuit, remember, which we said we'll keep using again and again, the recording circuit. So in this recording circuit, what we have here at the end is the output, right? So this is the signal that we got here. Now let's take this particular small component. Something is fed in to this component and we just get something out of this component. Let's say there is a voltage signal that is fed in at this point. Okay. That becomes the input to this component. So this entire component processes that input somehow and then produces some other output here. So you can connect your oscilloscope here and then see what is being fed as the input to the system. Connect your oscilloscope here and then see what is the output that is produced by the system. What does this system do? We know that it is a capacitor, it will block DC. So this system basically takes the input, blocks the DC in this input, that is the processing it does, and then produces an output without any DC voltages or DC current. So that is the role of this system. But as you can see, there are many components here, and then we just analyze only one block of it as a system. So the entire thing that we had here there could be seen as a system. So this is one block, this is a system, this is a system, this entire thing is another system. This entire circuit takes in an audio signal and produces an electrical signal which corresponds to this audio signal, right? So and then we could break that down into smaller and smaller systems, which becomes easier for us to analyze. So that is what we'll do in this course. We'll understand how to break things down into smaller and smaller systems. For example, let's take an audio equalizer. What is an audio equalizer? You take an audio signal as an input to this equalizer and then split that into low range frequency, mid range frequency, high range frequency. Low range frequency probably could be like a bass signal, and which corresponds to, let's say, drums kind of equipment. Mid range is something like voice kind of signal, and high range could be something like percussion, string kind of signal, right? Now we want to, let's say, amplify the amount of voice that we get in the audio, then we typically end up increasing the gain of the mid range filter. Or if you want to have higher bass, then you increase the gain in the low range filter, right? So this is what an equalizer does, and we might have all used audio equalizer in our phones and in all our in all your speakers and so on. So what effectively this system does is just take an audio signal, process it somehow, and then gives us the equalized signal. But what goes on inside that? There are multiple systems, and we break that down into multiple smaller systems. Basically, it starts with a buffer. After that, the buffer feeds to 3 different filters, and the 3 different filters produce an output, which is basically a filtered signal. and for each filtered signal is amplified in a different manner, and then they are all added up together. So you can break this down into smaller and smaller blocks. Each of this block is a system which will take a particular input and then produce some output. Okay. As you can see here, different ways of connecting this. So the moment you have multiple building blocks, you can connect them either in parallel. So these are all parallel connections, and you can connect them in series. So this is a series connection. So there are multiple ways, multiple combinations of parallel and serial connections that you can use with these building blocks and then build a bigger system. Okay. Once you build this system, you have achieved some way of processing the signal that is fed as the input and producing the output. If you want to analyze the system, you can go to these smaller individual blocks, these building blocks, and then we can analyze them separately. So if you want to analyze this entire system, it's not necessary that you have to know everything end to end. You can just take one block, analyze it, and then the moment you know how to analyze it, you can optimize it and then get the best possible design. Okay. Now, for example, you'll take the small building block there, a filtering circuit. How do we analyze this? Now, if we want to analyze this, we know that there is a signal that is going as the input and something that's coming as the output. An example of a filtering circuit is this capacitor, right? So we fed in some input here, we got some output. The processing was that the system blocked the DC component. So this is the processing it does. So we first need to understand what all is present in the input. If DC is not present in the input, then there is nothing to block. So we need to first understand how to analyze these inputs and outputs, right? So which means we need to analyze signals. So how do we analyze signals? How do we model these signals? How do we understand what is the frequency component in it? What are the different kinds of frequency components? How to separate them out? How do we understand these signal representations? How to analyze that? And you feed something here as the input, the system does something, some processing, transforms that to the output. That processing is what we refer to as transforming the input to the output. Now, how is this system transforming this input to the output? So, this is system analysis. So, we need to understand how to first model the system. So, we are feeding in a function here, and then we are getting another function here. Now that we have modeled the signal, how to model this transformation, the transformation that the system does on top of this input signal to get the output. Now, once we understand how to model this transformation, how to optimize this transformation. If we know how to optimize this, basically it means that we know how to design it. So what is the design? Here in this particular example, what should be the value of the capacitance that I should put? So if I know the relationship between this input and output, then I can tell what should be the appropriate processing that is going on inside. So if I know what should the appropriate processing be, then it means I know what should be the right capacitance value that I should plug in. So from this analysis of signals and from this analysis of systems, what we learn is how to design the system, how to know what are the properties and characteristics of the system. Once you know the properties of the system, then you know what is the right property that you're looking for, and you can tweak the system or you can design the system such that it has the property that you're looking for. So this is the entire goal of signals and systems, to break down any practical circuit into smaller systems, and the understanding of the input and output as different kinds of signals, and you know what you are expecting at the output. Now you will design the system such that it has the properties that you're looking for, and signals and systems helps us to do this.